Hello everyone, welcome to S Mathematics. In this video we will see group theory part 3, that is composition table and problems. Till now in group theory part 1, part 2, most of the examples I have given are infinite sets, that is set of natural numbers with respect to addition, set of natural numbers with respect to multiplication, set of integers with respect to addition, set of real numbers with respect to addition, set of real numbers with respect to multiplication, like that, set of rational numbers, set of complex numbers, like that. Most of the problems we have seen infinite groups. What is the distinction between infinite groups and finite groups? If the number of elements in the group is finite, then that group is said to be finite group. If the number of elements in the group is infinite, then that group is said to be infinite set, infinite group. Okay, basing on the existence of the number of elements in the group, we are going to see the whether the given group is infinite or finite. If the number of elements in the group is finite, it is finite group. If the number of elements are infinite, it is infinite group. Previously, in both the videos of group theory part 1, part 2, we have seen all the examples, major of the examples are only infinite groups. Now we will see finite groups. With that, to study the properties of finite groups, we are using an important tool called composition table. Okay, now see what is a composition table. Group theory part 3, composition table and problems regarding that. Okay, now see composition table. A binary operation in a finite set can completely be described by means of a table. Suppose if you had taken a finite set, see girls, see here, I am mentioning the set is finite. If you take any finite set, in that finite set, if you are able to define an operator, that is either addition or multiplication or addition modulo or multiplication modulo. What is addition modulo? What is multiplication modulo? I will explain to you for later. Now, completely be described by means of a table. That table is known as composition table. This table, composition table, the other name is K.L. table. Why K.L.? K.L., he is the Greek mathematician. He invented this group in, I think, in 1854, I think. As far as I am not correct, I remembered correctly, it is in 1854. On his name, it is also called as K.L. table. This composition table helps us to verify most of the properties satisfied by binary operators. What do you mean by binary operator? Any operator which is operated between two elements of a set and the result belonging to the set, then that operator is binary operator. Now after that, this binary operator may be associative. With respect to this binary operator, there exists identity in the group and there exists inverse for each element in the set. These are the properties with respect to the binary operator. So these composition tables will help us the properties which are satisfied by the binary operators are satisfying or not. We can verify using this composition table. Okay, this table can be formed as follows. See, we will see one example how to form the table. Now see how to form the table. For example, now what we said, the composition tables are meant for finite groups. So take one finite group, that is, take for example with 5 elements 0, 1, 2, 3, 4. These are the 5 elements. Composition table is taken with the 5 elements, and for the group, this is 1, 0, 1, 2, 3, 4. Instead of group, it is more proper if you take it is a set with a binary operator. It is not a group. Okay. Now for example, the composition table for the set 0, 1, 2, 3, 4 for the operation addition is given below. Okay. Now how to write the composition table team? Now take all the elements 0, 1, 2, 3, 4. Write them as first row 0, 1, 2, 3, 4. Similarly, in the same order, in which order you have written in the row, write in the column also 0, 1, 2, 3, 4. After that, observe the operation. Here what is the operation given to you? Addition. So write it as plus the coordinate. Okay. Now you got the first row and first column. Is it? Now the 0 plus 0 will be the first element of the body of the table. This is called as the body of the table. Now 0 plus 0, that is first row, first element, first column, first element should be added. That is 0 plus 0 will be written here. Similarly 0 plus 1 is here. 0 plus 2 is here. 0 plus 3 is here. 0 plus 4 is here. Okay. You have finished. Next, 1 plus 0, 1. 1 plus 1, 2. 1 plus 2, 3. 1 plus 3, 4. 1 plus 4, 5. Okay. Next, 2 plus 0, 2. 2 plus 1, 3. 2 plus 2, 4. 2 plus 3, 5. 2 plus 4, 6. Similarly, 3 plus 0, 3. 3 plus 1, 4. 3 plus 2, 5. 3 plus 3, 6. 3 plus 4, 7. 4 plus 0, 4. 4 plus 1, 5. 4 plus 2, 6. 4 plus 3, 7. 4 plus 4, 8. Now, you have completed the table. This is the composition table for the set 0, 1, 2, 3, 4 with respect to the operation addition. Okay. Now, if you observe how you are filling the entries of the body, you are filling the entries of the body by adding the corresponding row and column elements, because it is addition. If it is multiplication, you will multiply and write. Now 0 plus 0, 0. 0 plus 1, 1. 0 plus 2, 2. 0 plus 3, 3. 0. This row is called head row and this column is called head column. Is it? Now this is the column headed by 0. This is the column headed by 1. This is the column headed by 2. This is the column headed by 3. This is the column headed by 4. Similarly, this is the row headed by 0. This is the row headed by 1. This is the row headed by 2. This is the row headed by 3. This is the row headed by 4. Now suppose if you take the element 4 here, this element, this is, see here, this is 1, 2, 3, 4. First row, leave the first row. Leave it the first row. Now 1, 2, 3, 4. This is fourth row. This is, see here, third row, third column element. Is it? That is, you have to add the head of the third row and head of the second column. That is 3 plus 1 is 4. Is it clear? Now what is this? This is third row, second column element. See here, third row, be careful. Or fourth row, if you take, this is also considered. This is first 1, 2, 3, 4. This is fourth row, second column element. Is it or not? So that is the head of the fourth row and head of the second column should be added and you have to write here. Now is it clear? Is it clear how to write the table, how to complete the body of the table? Now you have to take this is the block. This is the block obtained by intersection of first row and first column. So first row head and first column head should be added and should be written here. Now, okay. Now if you observe the table, here there are some entries. See, if you see the first row, 0, 1, 2, 3, 4, all are the elements of the given set. First column, 0, 1, 2, 3, 4, all are the elements of the set. Now if you observe the second row, 1, 2, 3, 4, 5. 5 is not in the set. Is it? So if all the entries in the table are being in the table, in the set, then you will say that that set satisfies closure property with respect to this operation. Is it? Because here you are able to find out that 5, 7, 6, 5, 5, 6, 7, 8. These are the entries of the table which does not belongs to the table. Therefore, here the closure property is not satisfied. Okay. Now see the formally how we will write the formation of table. In the above example, the first element of the first row in the body of the table is 0. That is, see here, this one, this is 0. That we have written. And it is obtained by adding the first element 0 of the head row and the first element 0 of the head column. See here, what I said? This is the column head 0. This is the row head 0. These two are added and you have written. This is the second column, head is 1. 0, first row, head is 0, 0 plus 1, 0. I think it is clear. Similarly, the third element of fourth row is 5 is obtained by adding the third element 2 of the head row and the fourth element of the head column and so on. Already I explained to you. Is it clear? Now, the operation represented by composition table will be binary if every entry of the composition table belongs to the given set. Now see here, I showed you 5, 6, 5, 6, 7, 5, 6, 7, 8. These are not belonging to the given set. Therefore, here the addition you have taken, that addition with respect to that composition, the given set is not closed. That you have taken. Next, it is to be noted that composition table contains all possible combinations of two elements with respect to the operation. If this table says you will all the possibilities, you are having 5 elements, how to add two elements at a time, all the possibilities are covered under the table. Okay, now see the next one. Write the elements of the set in a row as well as in a column. We have written, no, like that. Now, order, it should be noted that the order should be maintained. Now, write the element associated to the ordered pair AI, AJ at the intersection of the row headed by AI and the column headed by AJ. Already I have showed you. Now, thus, ith entry to the left into jth entry to the top will be the entry where ith row and jth column intersect. Okay. Now, note, you should be noted that the elements of the set should be written in the same order both in the top border and the left border of the table. Okay. Generally, a table which defines a binary operation dot is if the composition is dot, you will call it as multiplication table, and if the composition is plus, you will call it as addition table, addition tab, otherwise you can write. Now, with I'll give 2 simple examples. With these examples, you will be able to understand better the composition table. Now, I think all of you know the cube roots of unity. What are the cube roots of unity? Cube roots of unity are denoted by 1 omega square, and omega cube is equal to 1 is the cube root of unity. Is it? That you have to remember. Prove that the complex cube roots of unity form a commutative group under multiplication. Now, with the help of composition table, we will see. Now, write the 3 elements in the top row and in the left row in the same order. That you have to remember. 1 omega square. In the same order, here also you have to write 1 omega square. You are able to write. After that, you have to fill the entries. Here, suppose with respect to multiplication, dot is the operator. 1 into 1 is 1. 1 into omega is omega. 1 into omega square is omega square. Omega into 1 is omega. Omega into omega is omega square. Omega into omega square is omega cube. But omega cube is 1. Okay. Similarly, omega square into omega square, 1. Omega square into omega cube. Omega cube is 1. Again, omega square into omega square, omega to the power 4. Omega to the power 4 can be written as omega cube into omega. Omega cube is 1. This is 1 into omega. That's why I have written here omega. Okay. Now, if you observe the table, all the entries are in the set, given set. All the entries are there, 1 omega omega square. So by observing how to read the table, I am explaining here. See, if you are able to show all the entries in the body of the table, that is, this is the body of the table. All the entries in the body of the table belongs to the set, then you will say that closure property satisfies. Okay. Now, after the closure property, associativity, unfortunately, associativity is taken for granted for this composition table, because operation is binary operation. Associativity deals with 3 numbers. So, it is not explained in this table, but in all the examples of composition table, we will take it is for granted. Okay. Now, associativity follows, we will say, that's all. From the table we observe identity element, how to find out the identity element. Now see here, if you take 1 omega omega square, now if you see the first row, 1 omega omega square, this is similar to the top row, see, head row. This is similar to 1 omega omega square. Similarly, this column 1 omega omega square, similar to this, that is 1. Now, suppose this 1 is the multiplicative identity, we got an idea in our mind. In each row and each column consists of this 1, means identity exists in the group. See, first row 1 is here, second row 1 is here, third row 1 is here. If you see the column, first row 1 is here, in first column, other than the head rows and head columns, first column 1 is here, second column 1 is here, third column 1 is here. Okay. Therefore, if each row and each column consists of the identity, then you will say that the group contains unique identity. After that, how to find out the inverse of each element? Inverse of each element. In order to find out the inverse of each element, observe the first row first. See, the identity element is here. Observe the second row, then here identity element. Observe the third row, identity element. Then, from the identity element, move to the top. The head of the column you will get, this is 1. Move to the left, this is head of the row. 1 is identity, 1 is inverse to 1. Similarly here, from this 1, move to the top, that is omega square, and move to the left, this is omega. Omega and omega square are inverses to each other. Similarly, move to the top, omega, move to the left, omega square. They are the inverses to each other. Okay. Now is it clear how to read? After that, commutativity also you have to read. In order to read the commutativity, draw the principal diagonal for this. That is the principal diagonal. Is it? Now after drawing the principal diagonal, now see here, here is omega and here is omega. Here is omega square 1, omega square 1. The elements should be symmetric about the principal diagonal. Then the group is said, the set is said to be satisfying abelian with respect to the given operator. Now see here, all the entries are in the given set. So closure satisfies. Associativity for granted. Okay, associativity satisfies, we will assume. After that, each row and each column is containing identity element 1. So identity exists. After that, finding the inverse to each other. In each column and each row, find 1 and move to the top and left. The head of that top and the head of the left row will be inverses to each other. After that, commutativity. Draw the principal diagonal, verify whether the elements are positioned in symmetric manner or not. If they are in a symmetric manner, it will be an abelian group. I think now the composition, how to read the composition table, I think it is clear to you. Okay, now we will see the same one. From the table, 1 is the inverse of 1, omega square is the inverse of omega, omega is the inverse of omega. Similarly, from the table, a dot b is equal to b dot a for every a b belongs to G, From the table, all the axioms of abelian group are satisfied. Therefore, G dot is an abelian group. Now, see the next property. This is the fourth roots of unity. This is 1 minus 1 I minus I. Now, with respect to multiplication, we will come. This is the set of fourth roots of unity. With respect to multiplication, we will see the table. That is, first write the elements in the top row, 1 minus 1 I minus I. In left column, 1 minus 1 I minus I. Here, because the first row and first column, as it is, you can write 1 is the multiplicative identity. So, 1 into 1, 1, 1 into minus 1, minus 1, 1 into I, 1 into minus I is minus I. Similarly, minus 1 into 1, minus 1, minus 1 into minus 1, plus 1, minus 1 into I, minus I. Now, see again the table. Now, this is the group G with elements 1 minus 1 I minus I, which are called fourth roots of unity. Now, draw the table. First, write the top row as it is 1 minus 1 I minus I. Left column 1 minus 1 I minus I. Now, complete the table. How to complete? 1 into 1 is 1. 1 into minus 1 is minus 1. 1 into I is I. 1 into minus I is minus I. Minus 1 into 1 is minus 1. Minus 1 into minus 1, 1. Minus 1 into I is minus I. Minus 1 into minus I is I. Similarly, I into 1 is I. I into minus 1 is minus I. I into I is I square. I square is equal to minus 1. I into minus I is equal to minus I square. Minus into I square is minus 1, that will be plus 1. Similarly, minus I into 1 minus I. Minus I into minus 1 is plus I. Minus I into I minus I square, that is 1. Minus I into minus I minus plus I square, that is minus 1. Now, observe the table. All the entries are belonging to the set. In first row, 4 elements, they are in the set. In second row, 4 elements in the set. Third row, they are in the set. Fourth row, they are in the. Similarly, columns. First column, second column, third column, fourth column. If you verify, all the entries are in the set. Therefore, with respect to multiplication, closure satisfies. Okay? Closure satisfies. After that, associativity is for granted. Take it. Associativity satisfies. Then, observe whether the identity exists or not. Now, verify each row. Here 1 is there in the first row. Second row 1 is there. Third row 1 is there. Fourth row 1 is there. Similarly, in first column 1 is there. In second column 1 is there. In third column 1 is there. In fourth column 1 is there. Is it? Therefore, each row and each column is there exists 1. So, that will be the identity element. Identity is existing. Now, find out the inverse. In order to find out the inverse, what you have to do? In order to find out the inverse, now say take the first row. Now find out where the identity element is existing. Here identity element is existing. Move to the top, 1 is there. Move to the left, 1 is there. 1 is inverse to 1. Is it? Like that you have to take. Now see the second row, 1 is here. Move to the top, minus 1. Move to the left, minus 1. Minus 1 is the inverse to minus 1 with respect to multiplication. Similarly, see the third row, 1 is here. Move to the top, minus I. And move to the left, I. I is the inverse to minus I. Similarly here, move to the top, I. And move to the left, minus I. Minus I is the inverse of I. Is it? So, you are able to find out closure property satisfies, associativity for granted, identity exists, inverse also you are able to find out. After that, you have to verify whether commutativity satisfies or not. Draw the principal diagonal. This is the principal diagonal. If you draw the principal diagonal and see the first row elements, minus 1 I minus I, minus 1 I minus I, minus I 1, minus I 1, 1, 1. So, the elements are placed symmetrically along the principal diagonal. Therefore, abelian property or commutative property satisfies. Therefore, fourth roots of unity satisfied. Is it clear? This only clearly explained. From the table, 1 is the inverse of 1, minus 1 is the inverse of minus 1, I is the inverse of minus I is the inverse of I. From the table, that is along the principal diagonal, all the entries are positioned symmetrically. Therefore, you can say that A dot B is equal to B dot A. From the table, all the axioms of abelian group are satisfied. Therefore, G dot is an abelian group. Okay? Thank you.